Chapter 7, Section 2, Verifying Trigonometric Identities. This is another one of the lessons that we've already seen in class before spring break. But again, recording these things so that way you guys can have these available for study, especially my dual enrollment students who will have an STC exam over sections 7.1 all the way through 7.4. There'll be a separate test for section 7.5 on to a little bit into chapter 8, which we'll talk about that later. But section 2, we've already seen this in class. I'm going to skip over the strategy stuff just like I did in class. Those we'll see with each individual problem that we're going to go over. There's going to be some problems that we'll skip over just like we did in the last video. We only did one problem, but there were 3 total problems in that first video, and 2 of them I skipped over, and I skipped over those in class, I think, too. There might have been 1 that I did do. But in example 1, and it gives us a suggestion up at the top, verifying identities by working with one side. That's usually the way that we go. And I'm going to try to do that for each of these examples. So not just example 1. So for example 1, verify that the following equation is an identity. Secant theta times sine theta plus cosine theta is equal to tangent theta plus 1. You want to work with one side and one side only. And by rule of thumb, usually the best advice is to go with the side that looks uglier, that looks more complicated, more complex. And in this case, I'm pretty sure you would agree. The left-hand side looks more complicated. So it's a lot easier as a strategy to go with the uglier looking one and simplify it down to the smaller looking one or the less complex looking one. So this one, secant theta times sine theta plus cosine theta, because we have parentheses with the sine theta plus cosine theta being multiplied with the secant theta, those parentheses are almost demanding to have a distribution operation done. So we'll go ahead and distribute the secant theta into both of those terms. And on the left-hand side, well, let me write it over here. Secant theta times sine theta plus cosine theta. And I'm going to say that it's equal to, I'm not going to write the other side of the equation. I'm not going to assume that it's true. I'm going to set it up for some extra work on the right side of this equal sign. So secant theta times sine theta plus cosine theta, if distributed out, secant theta sine theta plus, again, secant theta, but in this time it's times cosine theta. So here we have 2 terms, and each of those terms has a product. The first product, secant theta times sine theta. The second product is secant theta times cosine theta. Now, when brainstorming ideas, there's lots of things you can try doing, and that's probably the stuff that I skipped over in the strategies portion. But you look to see if you can find any reciprocal pairs, especially if there's products. One of the nicest things that can happen if you have 2 things being multiplied by each other, if you happen to get a reciprocal pair, those can cancel each other out and just equal to 1 in the end, which I think we do have a reciprocal pair. The second of the 2 terms, secant theta, cosine theta, that's a reciprocal pair. So let me write this down on the side really quickly. I'll probably do a vertical bar here, and on the side, we know that secant theta is equal to 1 over cosine theta. That is, they are reciprocals of each other. Now, a mathematical truth is that if you multiply 2 reciprocals, you end up getting 1. So what we're doing is we're taking 1 over cosine theta times cosine theta. What you end up getting is the same thing as cosine theta divided by cosine theta. The cosine theta in the bottom is the same thing as the secant theta on the outside of that fraction. So it's in essence the same thing as cosine theta divided by cosine theta, which that just equals to 1. So that's, I think, if you go ahead and take a peek back at what we're supposed to get, the right-hand side of the original equation, tangent theta plus 1, there we have our plus 1, it looks like. So what that also means, if I'm going to cheat a little bit, secant theta times sine theta is supposed to equal to tangent theta, and you might already see how. And I might be using the exact same property for replacing, or the exact same strategy for replacing secant theta. Secant theta is 1 over cosine. So that's 1 over cosine theta times sine theta. And that's the same thing as, if I write that as a single fraction, 1 over cosine times sine, that's the same thing as sine over cosine, which we understand sine over cosine, that's the second half of the tangent quotient identity. Let me write that down over here on the side. Tangent theta is equal to sine theta over cosine theta. That's what we're basically invoking. So anything on the right side of that vertical bar that I drew is an explanation of what I'm doing from one step to the next, maybe. Sine theta over cosine theta is going to equal to then tangent theta and then plus 1, which is exactly what we were supposed to get. So I'm going to put a check mark on that. So there's example 1. So what we ended up doing was working with the left-hand side. And again, because the left-hand side looks more complicated, the idea is if that one looks more complicated and might be more doable, I might be able to see a nice and easy way to simplify it down to the other one, the one which I almost completely ignored. It wasn't 100% ignored because I used it to gain ideas about halfway through as to where I was supposed to go from here. We matched up to see if I can see corresponding terms, like namely the 1, that plus 1 that we got in that first simplification. Okay, so example 2. Example 2 is very similar, it looks like. And here we have cotangent squared x times tangent squared x plus 1 in parentheses is equal to cosecant squared x. So there's several ways you might want to go about this. If I remember in the classroom, I have 4 different precalculus sections that I taught this section to, and pretty much each of those classes had different suggestions, or had students in each of those classes with different suggestions on how to do this, and none of them were wrong. So in the notes that I stored, there was more than one way to get this one done. If you wanted to follow exactly what we did in the previous one, that's going to be perfectly fine. It's going to lead you to an answer. It's going to lead you to the completion of this distribution, basically. So if you distribute cotangent squared into tangent squared x plus 1, you should be able to get the right-hand side. So cotangent squared x is going to, let's see, multiply times tangent squared x and then plus 1. And that's going to equal to, well, let me go ahead and distribute that out. That's going to be what? Cotangent squared x times tangent squared x plus 1 times cotangent squared x is just cotangent squared x. And that's what we get when we distribute the cotangent squared into that binomial tangent squared x plus 1. So then we brainstorm, look at both of those terms individually. I might not be able to do anything with the right term, but the left term is a product, cotangent squared and tangent squared. So here's probably where I might want to do some work on the side. You might already have some ideas. Do another vertical bar this way. And let's see. Like we had earlier, the first thing you want to be able to look out with is a reciprocal pair. And luckily cotangent, tangent are a reciprocal pair. Problem is that we have squares for both of these. So let's see. First off, I like the idea of using the reciprocal identity. Cotangent x is equal to 1 over tangent, and I put a square already. I'm getting ahead of myself. So 1 over tangent x. So this is without the squares. So I'd like to show that cotangent squared and tangent squared are reciprocals of each other, just like cotangent and tangent without the squares are. So the whole idea here is to square both sides. In order to square the left-hand side, we put a little 2 in superscript on this side. To square the right-hand side, we'll square it as a fraction. So 1 over tangent quantity squared. And if you remember, to square a fraction, you would distribute that power of 2 to both the numerator and the denominator of that fraction. So that's the same thing as 1 squared, which 1 squared is 1 times 1, and that's just 1. And to square tangent, you just write it in superscript. So that's 1 over tangent squared. I don't have to write the square on the 1. That's exactly what I wanted to show. So we're fine then to cancel those two out. Cotangent squared times tangent squared. Those two, just like in the previous example, should just become 1. So then the other term, which I have left over, I haven't done anything with that yet, cotangent squared x is what I'm left with. Now, it's a good idea between steps to compare what you currently have with what you're supposed to get. So I have 1 plus cotangent squared x. I'm supposed to have cosecant squared x, which if you're familiar with your Pythagorean identities, that's an easy one to show. That is one of the Pythagorean identities directly. 1 plus cotangent squared x is exactly equal to cosecant squared x. That's a Pythagorean identity. So I can go ahead and write that on the side. Pythagorean identity. So that's a Pythagorean identity. So this is equal to, and we can substitute what that's equal to based off of that identity. And we're done. So cotangent squared x times tangent squared x plus 1 is equal to cosecant squared x. So that's example 2. So we'll go ahead and move on. Example 3. Verify that the following equation is an identity. We have tangent squared t over secant squared t is equal to 1 plus cosine t times 1 minus cosine t. And this one, if you read the top where it says example 3, verifying an identity, it gives the same instructions working with one side. So this is probably one of those situations where if this is something you're trying or this is something that you're new to, this is the very first time that you're seeing these types of problems. A lot of the times on the side you can, or on a scratch sheet of paper, work on both sides simultaneously and see where they meet. And that a lot of the times can help you connect the dots on one side and one side only. So in this case, if I were to ask the question to my students, which of these looks uglier, I might get varying answers. Going back to that idea is you work with the more complicated looking side. And both of these look, in their own right, kind of complicated. So this is where it gets a little subjective. Which side do you believe is more complicated? The question then changes to, if there's no decision made, if the whole idea behind asking which one's more complicated, generally speaking, a more complicated expression can be simplified if you know your math into a more simple looking expression. Now, if they look equally complicated, then you try to see which of those two sides can you manipulate. Which of those are you more comfortable with manipulating? I'd expect a lot of my students to say the right-hand side is something we can actually manipulate pretty easily. Some of my students that are a bit braver and maybe or a bit more comfortable with the trigonometric identities might want to work with the left-hand side because they notice squares on these two trigonometric functions, tangent squared or secant squared, and either of those can probably be manipulated using a Pythagorean identity. So either or. I'm going to go ahead and go with the left since we want to practice using the Pythagorean identities anyway. So we have tangent squared t over secant squared t. I'll go ahead and write these over on the left. Then we'll set that equal to something, leave it blank, and those blank spots are going to be filled in with whatever manipulation steps we have to make. So tangent squared t over secant squared t, and it's really up to you. Tangent squared t over secant squared t, there might be a better way to do this than the way that I was thinking. I was referring to Pythagorean identities, and I might not need to go that route just yet. A lot of the times it's easy to, or it works, or it helps to replace each of these functions with an equivalent that's based on sines and cosines only. For example, tangent squared. First off, tangent we know can be written using the quotient identity as sine over cosine. Therefore, I can say tangent squared is the same thing as sine squared over cosine squared. And that right there is just tangent squared. So that's not finished, me writing an equal sign on that. I still need to do the same thing, but for secant squared. And let me go ahead and draw a vertical bar on the side and stating what steps we've already used. So tangent t is equal to sine t over cosine t. Now, if I wanted to find out what the expression is for tangent squared, you can square both sides of that. So tangent squared is equal to, in this case, this is sine t over cosine t squared, and that's the same thing as sine squared over cosine squared for your angle t. So it turns out that that's actually correct. Now, another thing we're going to end up doing, secant squared t. I have a bunch of sines and cosines for the numerator. I'd maybe like to change the denominator into sines and cosines as well, as we're able to. So secant t, this is, or secant squared t, this is 1 over cosine t squared. And of course, you would square the numerator denominator just like we did in the previous one, and this would be 1 over cosine squared t. And what we'll do is we'll go ahead and replace that in here. Secant, and I wrote secant when I was supposed to write cosine. So that's cosine squared t, and that's the denominator. So that's just the first step. Rewrite everything in terms of sines and cosines is one of the go-to strategies. A lot of the times it's like a backup strategy if you can't see anything directly. So sine squared t over cosine squared t divided by another fraction, 1 over cosine squared t. So what we'll do is we'll treat this as a division problem, or as a multiplication problem. You're dividing two fractions. It's best to treat division of fractions as the multiplication between modified fractions. You don't have to modify the first fraction when it's on top. So that one stays as is, sine squared t over cosine squared t. If you change the operation to multiplication, you have to modify the second. And by second, you mean the denominator expression. So what you're going to do is you're going to take the reciprocal of 1 over cosine t. The reciprocal of any fraction is you replace denominator with numerator, numerator with denominator. So it's going to be cosine squared t on top over 1. So those are the same thing. So then, here we have two fractions that need to get multiplied. When you multiply two fractions, you multiply across. Everything in the numerators will get combined by multiplication. Everything in the denominators will get combined by multiplication. Once we multiply, if there's any common factors, we can cancel those out. But you can go ahead and cancel out common factors before you do the multiplication step. And in this case, we see cosine squared t are common factors. They're going to end up canceling out anyway, so we can go ahead and cancel them out now. And you end up getting sine squared t over 1. Which that just simplifies to sine squared t. And this looks nice and simple, but if we remember correctly, that's not exactly what we have on the right-hand side. So we're really not finished. So we're not finished until we get exactly what we have on that right-hand side. That's this right here. So I'd like to get that. 1 plus cosine t times 1 minus cosine t. So we don't have exactly what we want. The sine squared t is supposed to be a 1 plus cosine t times 1 minus cosine t. The nice thing to point out is that we have an expression for sine so far. This is what we currently have. What we're supposed to get has only cosines in it. So we'd have to start thinking about, well, what's a way that I can get a cosine out of a sine? Which in the previous section, the way that we did that, if I wanted to get a cosine directly from a sine or a sine directly from a cosine, you would use a Pythagorean identity. And Pythagorean identity is pretty simple to use here since we already have a sine square. There's an exponent of a 2 on the sine. So if you remember, sine squared plus cosine squared for any angle must equal to 1. So therefore, sine squared on its own is 1 minus cosine squared of the same angle. So this is all coming from the idea that sine squared plus cosine squared is always equal to 1 no matter what the value of t is. So let's see, sine squared t is equal to 1 minus cosine squared t. And again, what I'm doing is I'm looking at what we're supposed to get and comparing that with what we currently have. How does 1 minus cosine squared t equal to 1 plus cosine t times 1 minus cosine t? It's easy to see, or hopefully it's easy to see. 1 minus cosine squared t is what we call a difference of squares. That is a binomial. Even though we have a cosine in it, hopefully it's not too complicated, but that cosine is getting squared. 1 is technically a square number, 1 times 1. We have a difference of squares, so it's 1 squared minus cosine squared. So we can think of this as a squared minus b squared in the general case, so a squared minus b squared. The difference of squares factorization scheme is a minus b, a plus b. The order doesn't matter. You can have a plus b first and then a minus b second. because the order in which you multiply two quantities doesn't matter. Multiplication is commutative. So sine squared is equal to 1 minus cosine squared t, which I'm working with just the 1 minus cosine squared t. That should factor out as 1 minus cosine t times 1 plus cosine t with no squares on them, and that's according to what I just wrote over here on this side. So those two are equivalent. So in this case, we took a to equal to 1 and b equal to cosine t. So that way, if you took a squared minus b squared, you get exactly 1 minus cosine squared, like what we started out with. And then if you plug it into the right-hand side, a minus b, a plus b is exactly 1 minus cosine, 1 plus cosine. And that's it for this particular example, number 3. Now you notice it's not the exact same order. 1 plus cosine's first. That doesn't matter. The order in which you multiply those two, but we get exactly those two factors, 1 plus then the 1 minus. So it's exactly what we wanted. I'll go ahead and put a check mark on that. Example 4. So again, verify that the following is an identity. Secant plus tangent over sine, all of that for x, is equal to cosecant x divided by secant x minus tangent x. So looking at this one, these two expressions, one on the left-hand side, one on the right-hand side, arguably the same complexity level. So they look about the same with regards to how complex they look. So then which side do I take? There's a Pythagorean identity that link tangent and secant together. So I'm just going to write that one down. That is secant squared x is equal to, and I didn't write it in the order that we saw it in, tangent squared x plus 1. That's a Pythagorean identity. That's one of the three that we saw in the previous section. But then what do I do with that? So secant squared is equal to tangent squared x plus 1. There's several things we can probably do with that. So what I'm doing is basically what I would be doing on the other side of a vertical bar like I did in the previous examples. We're messing with this just a little bit. So what I'm doing is basically I'm taking a timeout from the problem itself and I'm just messing around with the Pythagorean identity to see if I can come up with something that shows up in either of those two sides of the equation that's supposed to be an identity. So I notice that secant and tangent are together in either of the occurrences of secant and tangent on the left or right. So I might want to go ahead and subtract the tangent squared to both sides. So that way I get secant squared x minus tangent squared, and that's going to equal to 1. And then looking at that for quite a long while, because I don't have any squares on the actual equation that we're supposed to verify to be an identity, then there's a couple of things we can do. Secant squared minus tangent squared, going back to what we just saw earlier, the difference of squares, that might help us out here. I notice that is also a difference of squares on the left-hand side, not the right-hand side. The right-hand side is just 1. But on the left-hand side, secant squared x minus tangent squared x is definitely a difference of squares. So I can factor the left-hand side. And if I factor that properly, secant x minus tangent x in parentheses, that's a minus b. I need a plus b. So that would be the exact same secant x, in this case plus tangent x. And when I multiply both of those, I'm supposed to get 1. So there are the two binomials that I see in this supposed identity. So secant plus tangent, secant minus tangent. So that I like. That might help me out just a little bit. So because I can work on either side and both of them look equally complex, I might want to just work with the left-hand side. It doesn't really matter. It's on the left-hand side. So the way that we can do this is I might want to force in some factors by multiplication on top and bottom. So I'm going to work on the left, like I said, secant x plus tangent x divided by sine x. And that's going to equal to something. Now, before I put down an equal sign, what I'd like to do is, like I said, force in some factors in there that weren't there already. So I'm going to multiply that extra little thing that it wasn't there, but that I see on this other right-hand side of that vertical bar. So I'm going to go ahead and multiply in there what's missing. Secant x minus tangent x. Now, in order for me to multiply that in there, I need to multiply both to the numerator and the denominator of this expression, assuming, of course, that these two quantities aren't equal to each other, in which case you'd have division by 0. 0 divided by 0 can't be multiplied as a factor. So we'll just go ahead and put that as an assumption. We're just going to assume that that's not 0, that they're not equal to each other, secant and tangent. So secant x minus tangent x over secant x minus tangent x. That's going to get multiplied into both of these. And that's going to be part of the fraction now. Now, you would multiply the numerators together, and we've already seen that if I multiply those two expressions, we're supposed to get 1. So 1 in the numerator. In the denominator, though, I'm not going to distribute anything out just yet. Sine x, secant x minus tangent x, and this is all in the denominator. So I get 1 over sine times secant x minus tangent x. And again, once we finish up a line and simplify this part of the proof, you can go ahead and compare to what we're supposed to get, cosecant x over secant x minus tangent x. I see the secant x minus tangent x in the bottom, so that's good. Problem is I have a 1 on top and a sine on the bottom, and I only have a cosecant on the top. And those of you that know your reciprocal identities very, very well, this is easy from here on out. So what we just finished was the hard part, the most difficult part about this proof. So why am I saying that? The reason being cosecant x is equal to the reciprocal of sine of x. So 1 over sine x is cosecant x. That's a weird looking cosecant. It's still kind of weird, but it's a little bit better. So cosecant x is equal to 1 over sine x. And the idea here is that a sine on the bottom in a fraction is the same as a cosecant in the top of the fraction, or in the numerator of the fraction. And if you're not convinced, cosecant x on this left-hand side here can be changed to a fraction. So if it's not in the form of a fraction, you can force it to be a fraction by writing a 1 underneath. So that's a fraction on the left-hand side, cosecant is on top. On the right-hand side, sine is on the bottom. So a sine on the bottom is the same thing as a cosecant on top. So we can basically just rewrite that sine as a cosecant, but in the opposite side of the fraction. So cosecant on top, and then this remains in the bottom. And that's exactly what we were trying to prove. That's it for example 4. And if I don't remember, I want to see how many problems are left. There are 2 more problems, which number 6 I didn't do in class, and I'm not going to test you guys over number 6 anyway. So we'll look at number 5. And then we'll stop at number 5 for this one. So for number 5, verify that the following equation is identity. Same idea. Cotangent alpha minus cosecant alpha, cotangent alpha plus cosecant alpha is equal to 1 minus 2 cosine alpha plus cosine squared alpha, all divided by negative sine squared alpha. This one's another weird one. In this case, if you look at the right-hand side, 1 minus 2 cosine plus cosine square. There's a cosine square, there's a cosine no square, and then there's just a 1 with no cosine on it. That's a trinomial, a polynomial that's quadratic in cosine. On the bottom, you also have a square term and just a square term, negative sine squared alpha. But the top, the numerator, 1 minus 2 cosine plus cosine squared, that's the one where the interesting information's in. That's the one that's probably going to tell me what to do with all of this. Or I can completely ignore it and maybe use a strategy that we just used for the 2 previous problems on the left-hand side instead. Whichever you think is safer, whichever you think is actually going to produce some results, that's the way you want to go with. So maybe we're really, really comfortable with the difference of squares right now. We did that for the previous problem. And then for the problem before that one, maybe we're really comfortable with the difference of squares, and you notice that there's something that can be done with regards to that on the left-hand side instead. So any light bulbs that turn on right away, that's what you're going to want to go with. Try anything that comes into your head. If you fail, you fail. You can try something else. So cotangent alpha minus cosecant alpha, Notice how that's the exact same on the bottom except for the sign in between. So that's exactly what we want for a difference of squares. So what I'll do then is I'm going to multiply one of them to both top and bottom. Which one I choose I have to be careful with. So if I multiply the one with the minus sign on top and bottom, you're going to have the same sign on the top, which is not a difference of squares. That's what we call a perfect square. A perfect square is going to end up with 3 terms. And since I want 3 terms in the numerator, that's probably the way I want to go. You'll have a difference of squares in the bottom, which might work out. Because if I have a difference of squares, differences of squares might match up as a Pythagorean identity some way, somehow. And that's probably where we're going to get the single term for sine squared theta on the bottom. So I think I want to go that route. We'll multiply the minus 1 on both top and bottom. And what do I mean by that? So cotangent alpha minus cosecant alpha divided by, same thing except for a plus, cotangent alpha plus cosecant alpha is going to get multiplied by the exact same thing on the top, on both top and bottom. So cotangent alpha minus cosecant alpha, that's divided by the same thing, but this time the exact same thing. Cotangent alpha minus cosecant alpha. So what I'm doing is I'm adding in a factor, which is the same thing as what's in the numerator. So the reasoning behind that is I'm going to multiply out cotangent alpha minus cosecant alpha, and that's the same thing, or with itself, and that's going to be the same thing as if I had taken cotangent alpha minus cosecant alpha squared. That's in the numerator, though. In the denominator, though, we get that difference of squares quantity that we've been dealing with in the previous problems. So that's going to end up being, well, cotangent alpha plus, and then cotangent alpha minus cosecant. A plus b, a minus b is a squared minus b squared. So in this case, a is cotangent, b is cosecant, so cotangent squared alpha minus cosecant squared alpha is what we get on the bottom. So I haven't done much with the top except just I didn't want to write each of those factors twice again, so I just wrote the factor once with the square on top. So this is where we're going to want to remember our algebraic properties. So a plus b, actually it's not a plus, it's a minus. That could work with the plus sign all the same. A minus b quantity squared. This is one of the 2 types of perfect square trinomial formulas that we can go ahead and invoke. A minus b squared. If you remember your algebra, a squared minus 2ab plus b squared. And if we don't remember algebra, where does that come from? You take a minus b and you multiply it with itself, a minus b. You distribute a times a squared, a times negative b minus ab, negative b times a, that's negative ba, or you can rewrite it as negative ab, which that matches with this one. And then the very, very last, negative b times negative b is a positive b squared. So we're almost done. A squared minus ab, those 2 combine to exactly what we have on the top. A squared minus 2ab's, there's 2 of them, so we put minus 2ab and then plus b squared. So that's where that comes from. Okay, so I'm gonna use this property for the numerator of what we currently have. Equals, and on the top, cotangent alpha minus cosecant alpha, the whole thing squared. That's the same thing as cotangent squared alpha minus 2 cotangent squared cosecant squared. I forgot the alpha. Let me rewrite that because that looks like crap. So minus 2 cotangent squared alpha cosecant squared alpha, and then plus cosecant. Actually, no, those don't have squares on them. Plus cosecant squared alpha. And that's the numerator expression. So the stuff on top. This is going to be divided by cotangent alpha minus, or cotangent squared alpha minus cosecant squared alpha. And it looks like I'm nowhere near where I wanted to be. So if you compare those 2 fractions, cotangent squared alpha minus 2 cotangent alpha cosecant alpha plus cosecant squared alpha is supposed to be equal to or that's corresponding to a 1 minus 2 cosine alpha plus cosine squared alpha. On the bottom, we have a negative secant squared alpha, which that might be a little more confusing where that's going to come from. But let's see. What might help us out right now, if you look at that a little further, cotangent, cosecant, cotangent, cosecant. How are cotangent and cosecant related to each other? So that's probably the first question I would ask. How are cotangent and cosecant related to each other? There's a Pythagorean identity that links the two, the squares of the two, that is. And if we remember, 1 plus cotangent squared, let's say alpha, because we're using alphas in this case, is equal to cosecant squared alpha. Okay, that I already like. In this case, cotangent squared minus cosecant squared, if you look at the identity to the right, you should be able to see that that's a -1 right away. And where we get that from is you'd probably subtract -1 both sides. You'd get cotangent squared x is equal to cosecant squared alpha minus 1. But you could write the -1 at the end instead of at the beginning -1 plus cosecant squared. And not finished. Cotangent squared minus cosecant squared. And I had said that was supposed to equal to -1. You can see that clearly if you subtract cosecant squared on both sides. So cotangent squared x minus cosecant squared. And I'm writing x's, those are alphas. And that should equal to -1. So just -1. Cotangent squared alpha minus cosecant squared alpha is equal to -1. That's what goes in the denominator. So I'll have to rewrite all the junk at the top. So cotangent squared alpha minus 2 cotangent alpha cosecant alpha plus cosecant squared alpha. So basically what I was doing is working on the bottom as if I were ignoring, like, let's say the red elephant in the room. But I did get some simplification done. So that's a -1 on the bottom, and that the only thing that matches up here so far is that negative sign over here. So that's where the negative comes from. So we're kind of close. Now we'll see what else happens in this case. I'm supposed to get only cosines on top and a sine squared on the bottom. So if I have a expression that only contains sines and cosines, maybe it's a good idea to change the current expression in terms of only sines and cosines. So cotangent and cosecant can both be written as expressions with only sines and cosines in them. So we'll try it this way. I might want to extend this. Cotangent squared. We've seen this math already before in a previous example, cotangent squared. If you remember, cotangent is cosine over sine. So cotangent squared is cosine squared over sine squared. And I'm using x's, I should be using alphas. Alphas are pretty easy to get from x's, but it's not working out right now. Okay, so cotangent squared is cosine squared over sine squared. Cosecant, wherever I see a cosecant alpha by itself, which I see 1 by itself without a square, that's 1 over sine. I kind of like that already. 1 over sine, because I'm supposed to get a sine on the bottom. But anyway, plus the other term is a plus cosecant squared x. So cosecant squared, not x, alpha, is equal to 1 over sine squared for the same reason. So cosecant squared alpha is equal to 1 over sine squared alpha. What I'm going to do is I'm going to take all three of these quantities and replace them wherever I see them in that numerator. And that numerator is about to get a little uglier. So cotangent squared alpha is the same as cosine squared alpha over sine squared alpha minus, there's a 2, cotangent alpha, cosecant alpha by themselves. Oh, and I forgot the cotangent by itself, but it's pretty easy to see. It's cosine over sine times cosecant, which we wrote down as 1 over sine. Those are two fractions that are getting multiplied by each other. So if you multiply them together, you would multiply numerators, multiply denominators. You'll end up getting cosine over sine squared. If you look at the next term, plus cosecant squared is the same thing as 1 over sine squared. all divided by -1, which I'm going to leave that division by -1. In order to, one of the ways to simplify the division by -1 is to just change all of the signs in the numerator expression. But I want to leave that -1 there because that's the only thing right now that matches with what we currently are, or what we're supposed to get. But if I go ahead and take a peek, compare what I currently have with what I'm supposed to get, it's starting to come together a little bit. There's supposed to be a 1 minus cosine alpha plus cosine squared alpha. It doesn't look like it's in the right order, but there's some things there that correspond. So we'll see. Now the nice thing, like I was saying earlier, look at that middle term. Minus 2 cosine alpha over sine alpha times 1 over sine alpha. That can simplify into one fraction, which I'll go ahead and write that down a little bit. So that's cosine squared alpha over sine squared alpha minus 2. And as one fraction, cosine alpha over sine squared, and then plus 1 over sine squared alpha, all divided by -1. And we're getting pretty close. The nice thing about all three of these terms, they all contain a sine squared alpha in the denominator, and that's basically the last step, is dealing with that denominator, because that denominator contains a sine squared in the bottom. We're almost done. So cosine squared alpha, we'd like to take all of those fractions and combine them, since they all have the same denominator. Now, the only thing that might be keeping you from thinking all of these as fractions that I can combine is that 2 in the front, which I went ahead and erased that. I'm going to extend this fraction if I can. And you could write the 2 on top with the cosine alpha. So now I could think of these three fractions as having the same denominator, sine squared. So they all have identical denominators, and I can go ahead and combine these. When you combine fractions by addition or subtraction, you perform the addition or subtraction with the numerators only, and you preserve the denominator at the end. So it's going to be cosine squared alpha minus 2 cosine alpha plus 1. That's divided by the common denominator, sine squared alpha, and this is a fraction that's being divided by -1. Now, when you divide by -1, it's the same as multiplying by -1. Dividing by -1 or dividing by -1 or multiplying by -1 have the same effect. It just changes the sign on everything. So this is the same thing as just negative cosine squared alpha minus 2 cosine alpha plus 1 over sine squared alpha. Division by -1 is the same thing as multiplication by -1. The reason being, -1 is its own reciprocal. So to multiply by the reciprocal of -1 is the same as multiplying by -1. And we're almost there. If you compare this with what we're supposed to get, we are almost there. I literally just switch a couple of terms in the top, and then I can also just move the negative sign from the outside of the fraction into the denominator of the fraction, and that's mathematically legal. So I'll leave the numerator untouched for now. Cosine squared alpha minus 2 cosine alpha plus 1 divided by, and you could move that negative sign to the bottom with the sine squared, which is where I wanted it because I'm trying to show that it's equal to this thing, which has the negative on the bottom. Only problem now, cosine squared alpha minus 2 cosine alpha plus 1, it's in the wrong order. But I'm tempted to just check mark that and say it's done because it's basically the same thing. All I'm going to do is switch some stuff around. Now what would I swap? The negative term, they match. -2 cosine alpha are the same. The cosine squared alpha shows at the end, the 1 shows up at the beginning. So you're just swapping these two out with each other. And that's okay. The order in which we add or subtract mathematical quantities, if they're already signed, doesn't matter. So you just have to make sure that you keep the sign when you're swapping terms. So if any one of those terms was negative and you're moving it, you make sure you move the negative sign with it. If it was positive, you make sure to move that plus sign with it too. So in this case, you could just rewrite this as 1 minus 2 cosine alpha, because that was a minus term, and then plus, because it was a positive term, cosine squared alpha, all divided by negative sine squared alpha. That's exactly what we wanted to prove. This is the last example for this particular section, section 2. That concludes this particular lesson.